All right, why don't we get started? It is my pleasure to introduce Arsène Vasilyan. He's our new postdoc here at IFML, and depending on how things shake out at NSF, possibly the last. Arsène did his PhD and undergrad at MIT, and his advisor was Rubinfeld. I didn't know that John Kellner was also your co-advisor. Arsène and Renit invented the model of testable learning, which is one of my favorite papers of all time and has spurred and inspired us to do, and my students to do, a lot of follow-up research and a lot of follow-up models with Arsène. So it's really exciting to have him here. And he has a real sort of eye for elegance, both in coming up with definitions and models and also really slick proofs. So it's great to have you here for 2 years and take it away.
Yeah, thank you, Adam. So today I'll talk about our recent work about testing noise assumptions of learning algorithms. This is a very new paper. It's been put on arXiv just a few weeks ago. So, and it's joint work with Serbi Goel at UPenn, Adam Clivens, and Konstantinos Stavropoulos. So both of them are here. Let's start with some background of what it means to learn with some label noise. So what's the basic setup? So you have some learning algorithm. So it gets data set that comes from some distribution DIID, and it's labeled by some function that's not necessarily in your function class. So you have some function class, let's say halfspaces. And learning with label noise means that sort of this data set you get is not perfectly captured by one of those functions there. And so what you want to do is you want to compete with the best classifier in your class. So for example, you have some data set, there is no linear classifier that does perfectly on it, but you want to do approximately as well as you can. So if opt is the best error achievable by your function class. So you want to find a classifier that has an error of plus epsilon. So this is the
So just you're calling this label noise, but if I'm understanding correctly, it's just same setup if the labels are actually correct but don't fit the half.
Exactly. Yeah.
Okay.
Yeah. So this generalizes the sort of the basic case, the standard learning case where there is a classifier that perfectly describes it.
This is like the traditional statistical learning theory setup from the 70s.
Right, but it doesn't need it's whether it's noise or whether that's the true classes in this case. Yeah.
Okay, so, and I'd like to emphasize that today we'll be talking about computational aspects of this problem. And for many classes, the statistical aspects are very well understood. So if you are able to get a large enough data set and get a classifier that has so if you call error sub s, if that's the error on your data set, the empirical error, so you know that if your data set is large enough, then for every classifier, the error on your distribution is close to the error on your data set. So if you are able to minimize the error on your data set, or what's called empirical risk minimization, then the thing you would get would be also approximately optimal on your distribution. So this slide kind of summarizes the statistical aspect of the problem. And for a lot of function classes, we know exactly how large the data set needs to be for us to, for these two errors to be close to each other. Kind of when you start, so this is the picture when you only care about statistics, you only care about how many samples you get. But if you also care about computation, how much runtime you can do, the story becomes much more complicated. So this task of empirical risk minimization, of you give me a data set, I find a classifier in the function class that does approximately best on the data set. it's known to be NP hard in the worst case. And even if you assume that the data points are IID Gaussian, but the labels themselves are adversarial, worst case, then there are still hardness results for this task, even for the most simple class of half spaces in D dimensions. So it's known you can, assuming widely believed cryptographic assumptions, you cannot fit the best half space, even if you're in polynomial time, even if your data set, if the examples are IID Gaussian. Okay, so, and kind of in terms of optimization, this corresponds to the landscape, the optimization landscape being, having a lot of spurious local minima and difficult to optimize. So how can you get around this hardness results? So it turns out if you assume that the noise, the label noise is not worst case, is not fully adversarial, but it satisfies some assumptions, then you can get around this hardness results. So one very well-studied setting is the random classification noise. So there is so in this talk, we'll be mostly focusing on half spaces. So let's say there is a ground truth half space. And each label is, you get for each example xi, you get the right label with probability 1 minus eta, and you get, and the label gets corrupted, and noise gets added to it with probability eta. And a more general setting is so-called Massart noise setting that generalizes this random classification noise. So I'll say a couple words about these two models in the next slide too. So here, instead of just getting flipped with probability eta, an adversary gets an option to flip it or not. And that's this model generalizes random classification noise. And as a result of a long line of work, it was shown that if your examples are Gaussian and you have Massart noise rate of at most 0.5, let's say 0.49 or something, then you can do this learning task. You can get an approximately optimal classifier in time poly in dimension over epsilon. And let me show you an example of like what kind of, so in the next slide, I'll explain more about the relationship between Massart noise and random classification noise, RCN. Let me just show you some examples. So RCN noise rate of 0.3 means, every time you get an example, the label is the right one, probability 0.7, and it gets flipped with probability 0.3. So Massart lets you capture like this sort of situation. So imagine you have some region, like this blue region, where it always gets flipped with probability 0.3, but in some other region, like this green region, it gets flipped only with probability 0.2, and everywhere else it gets flipped with probability 0.1. Yeah, so this is a very natural type of setting that is not captured by the RCN noise model, but Massart noise does capture it. So you can check that you can set up this adversary in such a way. So this will be the flipping pattern, flipping probability pattern in your D-dimensional space. And this is in contrast with adversarial noise, where there could be some region where the adversary, the label always gets flipped. Yeah, so that's the type of thing that's not allowed under Massart noise. And surprisingly, like it seems that RCN and Massart, they look very similar, but it turns out that Massart is a lot more challenging to design algorithms for than RCN, because for RCN, you can do this thing where you can just run the algorithm for like a lot of classes. You can essentially run the algorithm that assumes there is no noise. And because the noise is so nice, it's like independent everywhere and it's the same rate. You can show that the noise cancels itself out if you average enough. And what you get is, the analysis of this regular no noise algorithm kind of transfers through. but these types of arguments get they really stop working even for these types of situations where the noise is not exactly the same rate everywhere, but it's like a slightly different rates in different regions. And that's what Massart is able to capture. Okay, so that's the overall background on learning with noise assumptions. So the upshot is that learning with adversarial noise, it's a so-called agnostic learning, where the noise is adversarial. Its worst case is a lot of times computationally intractable. But if you make assumptions on the noise, such as a Massart assumption or a random classification noise assumption, then what you can do, then a lot of times you have polynomial time algorithms for these tasks, and the problems become computationally tractable. But here's the kind of a question. So what if you are really worried, if you really care that your the classifier you get is epsilon optimal? Yeah, if it's like a really big deal for you, if it's not, then it seems you can say, okay, I've run this algorithm from one of those papers, and they have a theorem that says if I run their algorithm, then it will be epsilon optimal, so I can sleep at night. Yeah, but what if the noise is not Massart? Yeah, so all these theorems have as one of their premises the assumption that the more noise satisfies a certain noise model, for example, Massart. And if the assumption does not hold, then the conclusion of the theorem does not have to hold. So unless you are fully confident, so in order to use one of those theorems, you need to know for sure that the noise satisfies that assumption. And in this work, we are asking the question of, can we test this assumption? So can we, instead of just like having to believe it, can we do better? And here's the framework we propose in this work. So your algorithm or testable learner has so again, it gets your data set labeled by some arbitrary function, and it has two options. It can say accept and give a classifier f. So in this talk, we'll be mostly focusing on halfspaces. So that's one option, and the other option is to say reject. I think the assumption does not hold. Yeah, so these are the two options that the algorithm has. And what's the guarantees we want the algorithms to satisfy? So soundness, there are two conditions, soundness and completeness. So for soundness, it means no matter what data set your algorithm is given as an input, if your algorithm accepts, then you can be fully confident that the error of this classifier f is at most the error of this half space f you got is at most the best error you can get on your data set plus epsilon. So no matter what actually the distribution is or what the noise pattern is, if your algorithm said yes, accept, then you know for sure that the thing you got has error optimal plus epsilon. Okay, and completeness, it means that whatever those previous algorithms that learned with Massart noise do, then this algorithm also has to do. So formally, if your assumption actually holds, so if your data set, if your distribution on examples is Gaussian and the Massart noise assumption indeed holds on your labels, then with high probability your algorithm will have to accept and output something that has approximately the optimal error. Yeah, so and for the noise rate, this kind of assumption that's at most 0.49, it's the same assumption that those algorithms that just learn under Massart noise, just assuming Massart noise, they also have to make. So yes?
So if that condition doesn't hold, then it can reject or accept freely with no problem. Yeah,
exactly. So it either tells you Massart assumption doesn't hold, or you get the best classifier
If it
anyway.
does accept, whenever.
When it accepts, it has to be right.
It gives you a proof that it's correct.
Okay,
Yeah.
but if it's, if it rejects, it can, then that condition doesn't hold, it could have, there's
Just
no
doesn't reject.
assumption.
Yeah, it just says reject.
Yeah, and our main result is an algorithm that satisfies this this definition that also runs in polynomial time in your dimension and error parameter epsilon. And so the way I like to think about this is that you get some labeled data set S, and you either are told that the assumption didn't hold, that this Massart assumption doesn't hold, or you not only get a half-space F, but also a proof, a mathematical proof that the thing you got is epsilon optimal compared to all half spaces out there. Okay. So now, if you're very worried that your classifier is not optimal, then you don't need to be worried because, even if your noise was not Massart, but your algorithm still accepted, then you can be confident that the thing you got is indeed epsilon optimal. Yes?
That's a brain.
Yeah, that's a brain. Yeah?
Yeah, so I just want to double check. So are you also testing the data distribution?
Yeah, exactly.
So it's not only the noise distribution, but also the data distribution.
Yeah, thanks for the question. That's exactly true. Yeah. So yeah, it's kind of a fully end-to-end definition. So if you got accepted, if it accepts, then no matter what the actual data distribution was, as well as the noise pattern, if you received accept, then you know for sure that the thing you got is epsilon optimal.
They don't even need to be IID, right?
Yeah, it doesn't even need to be IID. Yes?
All right, I gotta be that guy. How big is the poly?
To the fourth, I believe.
Okay.
P over epsilon to the
Is it the same as the like non-testable learning setting?
Yeah, I think there it's like to the square.
Okay.
I think they have square and we have to the fourth.
I see.
Yeah.
I think the eta, the gap of eta with 1/2 is index 1.
Right. So that's a good point. So this is for some here. If you put like 0.1,
I see.
then it's to the
You
fourth.
put some exponent in how bad that.
Yeah, and that's
Approaches.
inevitable. Yeah. So like as this thing approaches 0.5, it has to.
But is it like an exponential dependence in the gap, or is it like 2.5?
I believe we know for a fact it has to be like polynomial, like d to the polynomial in the gap.
Okay.
Yes. But yeah, if this is like 0.1, I think you get like d to the fourth.
Okay, thanks.
Yeah, thanks for the question.
Yeah, Kevin, if you could improve that, it'd be great.
Sounds good.
Yeah, might break some crypto assumptions if you improve it too much.
Only in the gaps equals 0.5.
Yeah. Okay. Okay, so, and I like to compare it to some previous work. In some previous work, the thing we were testing was only the example distribution. Yeah, so the label noise was allowed to be arbitrary. And what we were testing was only the distribution on the examples. And so in that case, if that's what you wanted to do, then if your function class is half-spaces and the data point distribution is Gaussian, you either, if you insisted you need to run in polynomial time, then the error you got is some multiplicative constant times optimal plus epsilon. So you couldn't get this op plus epsilon error. You'd have to lose, maybe like the best error was 0.1, you would have to get like 0.2 plus epsilon. This was that type of dependence. And on the other hand, if you said, no, I want an additive epsilon error, I want a best half space error plus epsilon, then you couldn't run in polynomial time. So there were lower bounds here, even if you didn't have to test your assumption. So they had like, if you do not assume any if you don't make any assumption on the noise, you have this limitation. So this is true even if you, for like regular learning under Gaussian examples. And it's also, and our previous work matched those algorithms with testable algorithms that also give you proofs that the things you got is indeed satisfies this optimality condition. And the newer work matches, allows you both run in time poly d over epsilon and get an error O plus epsilon. So like this is the work that did it just assuming that the examples were Gaussian and the noise satisfied the Massart condition. And our new work lets you also gives the testable algorithms that also give you certificates that the thing you got is indeed satisfies this O plus epsilon optimality. Any questions? Okay. And yes, I would like to emphasize that testability allows you to make algorithm selection. So if you are not sure, like was the noise Massart or not, you can first learn learn this testable algorithm, and then if it works, great. If it doesn't, then you can say, then you know for a fact that the noise is probably does not satisfy the Massart assumption. So you can go ahead and run one of these algorithms. So either say, okay, I'm going to run for longer time because I really want this O plus epsilon error, or you can say, okay, I'll run this algorithm, I'll get some multiplicative error too. So it lets you make an informed choice, like which algorithm to run. And let me explain some of the main technical ideas that went into this work. So, and let's first focus on testing the RCN assumption. So I remind you, random classification noise just means you have random flips of your labels. So what you want is an algorithm, gets a data set, and soundness is the same. Like if it accepts, you should know for sure that the half space you got is epsilon optimal. And if your assumptions hold, so if your examples are Gaussian and the noise satisfies this RCN assumption, random classification noise assumption, then with high probability, your algorithm should accept. And yeah, so again, you have to assume that this is less than 0.5. And we show that if you require all the same thing, but you replace this 0.49 with 0.5, then this becomes impossible to do in polynomial time. So let me explain kind of one of the main ideas that go into this algorithm. So step one, you just run this algorithm that you know will work if your noise actually satisfied the RCN assumption and the examples were Gaussian. So you find this hypothesis that should be very close to the ground truth half space if the assumptions indeed held. So then you separate your examples into two sets, the S incorrect and S correct. Yeah, so S incorrect is going to be all the examples on which this classifier you just learned misclassifies it. It gives the wrong answer. Yeah, so here, if the red ones were +1s and blue ones are -1s, so you separate out the ones that your classifier was giving the wrong answer on. And here's what you want to check. So you want to make sure, you want to certify the following two conditions. So on one hand, so what you want to say is that for all W prime, so for all other half spaces W prime, not there are like infinitely many of them, this region where this other half space disagrees with the half space W you found should satisfy the following conditions. So on one hand, the fraction of points in S in your original data set S that fall in in this purple region where the two half spaces disagree should be at least something very close to what it should be if the distribution was indeed Gaussian. Yeah, so if the distribution was Gaussian, then each of these regions has very close to proportional to the angle between the two vectors, fraction of the examples in your data set. Right, so this is one thing you want to certify. And the other thing you want to certify is that out of the points that are in S incorrect, so the points, this orange points on which your classifier is misclassifying, the fraction of them that fall, again, for every W prime, for every other candidate classifier, there are not too many points in this disagreement region, in this purple region, where the half space defined by W and the half space defined by W prime disagree with each other. So again, if it's it should be at most something close to 1 times the angle between the two vectors plus some small additive error. So that's kind of the overall plan. What we do is we certify these two conditions, and let me convince you that if you know these two conditions are true, then if you know for sure these two are true, then you are able to prove that this W half space is approximately optimal. So how do you show that?
Why do you need to certify the first one? Because the first one is just like a statement of X being Gaussian.
Yeah, but we want to have a proof, right? So if your
So you want to
distribution,
have a proof of that and the fact that the noise is RCN, right?
yeah, the noise, you're right, the noise comes in the second one,
Okay.
but it's also like our algorithm, if the distribution is not Gaussian, it should not. So like if you look at the definition, if it's Gaussian, and it should accept. So if it's not Gaussian, then you cannot just assume that this is true, and then you might have a problem. Yeah, so you have to certify this thing as well. You cannot just assume it. So let's argue that if you are able to certify this two, then you have a proof that this half space W is approximately optimal. So, okay, suppose we choose some other W prime as our new half space. And this second condition tells you that you like moving from W to W prime will not fix too many mistakes. So you just substitute this in, and you see that the number of mistakes you fix by moving from W to W prime is at most 0.5 times the angle divided by pi plus epsilon. And this first condition tells you we will not make too many new mistakes. Excuse me, we will make a lot of new mistakes as we move from W to W prime. Yeah. So if you just substitute, you get this mistake rate will increase by at least this. So overall, if these two conditions hold, you are able to conclude that for any other half space W prime, you will be unable to gain more than O of epsilon in your accuracy rate if you move from W to W prime. Okay. So so then we'll discuss more in the next slides about how we certify these two conditions. But let me kind of give you an intuition why we expect like what can we say? So we know S is Gaussian. Yeah, so we know if the assumption holds, then this data set S is composed of IID Gaussian examples. But I claim that this is also approximately true for this data set S incorrect. So why is that true? So recall if the assumption indeed was true, then this vector W will be very close to the ground truth half space. And if that's the case, imagine if you recovered exactly the ground truth half space. Then let me make a drawing. So if you recover the ground truth half space exactly, then all the examples here, these ones are true. You get the right label with probability 1 minus theta, and you get the wrong label with probability n. And same with all the points here. So the points in this set as incorrect will have to, they're picked from Gaussian distribution, and they get added with as incorrect independently with probability n. So you expect, so if this W is indeed if you recover the ground truth linear classifier in this first step, then the distribution of the point in as incorrect will be exactly Gaussian. And you can show that if this is approximately true, if there's only a tiny error in your half space that you recover, then with this data set as incorrect will approximately be composed of Gaussian examples up to a small total variation distance. So kind of this allows you to conclude that, so basically we want this to be able to certify these two conditions for Gaussian data sets. So here's sort of one way to think about this. So this reduces to the following task. So someone gives you IID Gaussian data set, and you want to either give a certificate that for every vector W prime, this disagreement region, this region where the half space given by W and the half space given by W prime disagree with each other, has very close to the fraction of points that it should have, like the actual Gaussian probability mass. Yeah, so just so everyone's on the same page, if you have two vectors and you pick a random Gaussian example, then it falls in this red region with probability angle divided by pi, and it falls outside with probability 1 minus angle divided by pi. So you can show if you have a whole more than something like dimension many Gaussian examples, then for the AVC dimension argument will tell you that for all half spaces W prime, this condition will hold with high probability. And so what you want is you want to be able to certify, you want a mathematical proof that for this specific data set, this condition actually holds. Or you get your algorithm tells you that the assumption didn't hold, that your data set did not in fact come from a Gaussian distribution. So any questions about this? Thanks. So, and let me tell you how to certify a weaker property. So this is a bit intricate to show, but I'll be able to show you in a very high detail how to certify this weaker property that also allows a multiplicative error. Yeah, so you're given a Gaussian data set and you want to certify that so you're given a Gaussian data set and this vector W, and you want to certify that for all vectors W prime, the fraction of points in this region where the sign of Wx and sign of W prime x disagree, the fraction of point is at most some constant times the angle plus epsilon, right? And again, so just so everyone's on the same page, there are infinitely many vectors W prime that you want this to hold for. So, and even if you like all the brute force approaches that just look on a bunch of W prime, will have to look on exponentially many because there are exponentially many W primes in your space. So, okay. So first step is to say, okay, we want to show this for all W primes, but without loss of generality, you can assume that the angle between W and W prime is a multiple of epsilon. Because if you have this only for like this types of W primes, general W prime, you can just rotate it to the W prime whose angle is a multiple of epsilon. You know that this holds for that, and the red region for this W prime with bigger angle will be a superset of the red region for your previous W. So first step is you can assume this without loss of generality. And okay, now how do you certify now? So you have your data set. So you use iterate over all alphas in epsilon to epsilon and so on, multiples of epsilon. And what you do first, as you look at this blue region, where the projection of your data point on this vector W is at most something times alpha, at most alpha, and you check that you don't have too many points there, which should be true for the Gaussian distribution. And then you compute this matrix. So you compute the matrix X transpose times this indicator that your data point is outside the blue region, divided by this factor 1 over W times the inner product squared. So the things that are closer. So things inside the blue region don't count, but outside of the blue region, the closer you are, the smaller your projection, more you count in terms of this factor. So you have this matrix, and then you compare, then you check that in the positive definite ordering, this matrix you got is not much larger than it should be in expectation under Gaussian distribution. So you compute this and you check that the difference between the two is a positive definite matrix. So this is the algorithm. And it turns out that if you run this, so first of all, if your distribution is indeed Gaussian, you can check all of this all these tests will pass. So here you'll just need to use the concentration inequalities for matrices. So this matrix will be super close to this matrix. So this inequality will hold. And so the kind of the non-trivial part is the soundness. To show that if these tests do indeed pass, then you have this condition, like your data set will satisfy this probability for all W primes. Okay. So, so let me show this. Let me prove this in the slide. So here I copied the conditions that you check in the algorithm. So so we want to bound this fraction of points in this red region for all W prime, but there is a red region like this, and we want to bound the fraction of points that fall into that. So let's just bound this upper half. The lower half will have the same, will follow by the same argument. Okay, so you can take this blue strip that we discussed in the previous slide, and you can break this red region into, you can intersect it with the strip, and you can look at the rest. And we know, like, this first condition tells us that here you don't have more than O of alpha fraction of your points. And so now, and this is the definition of this upper part of the triangle that does not intersect with the blue strip. And yeah, the thickness of the blue strip is alpha. So now let's define. So let's call this part chi, and we can just rewrite it as the probability among all your points in your data set that this inner product is bigger than alpha, and this ratio of the projection on this divided by projection of this is bigger than 1 over the tangent of alpha. Yeah, so this is, so I literally rewrote that. And then you can use, we can recall the definition of this matrix M alpha. It allows us immediately to use the Chebyshev inequality to bound this value chi by alpha squared, tangent alpha squared, which is up to a constant alpha squared, times this W, this vector transpose times this matrix times this vector. So this is, again, you just substitute the definition of this matrix here. And you see that this quantity is this thing is the expectation of this thing squared. So you go ahead and then you can substitute this inequality that we checked for our test into this, and you get this expression. So alpha squared times what this expectation of this quantity should be under Gaussian distribution. And then you can just, this is just a one-dimensional expression. You can compute what this exactly equals to for the Gaussian distribution, and it turns out this equals to 1 over alpha. And overall, you get a bound of O of alpha for this probability, the fraction of points that fall in this red region over here. Yeah, so as a summary, so what we did, we tested this, so our tester checked that a certain matrix, so the most substantial part of the tester checked that a certain matrix is positive definite, and that allowed us to conclude that for all W primes, we have this condition. The fraction of points here is bounded.
So we have to look at the singular vectors of that matrix,
Vectors?
the singular values. Of that
Yeah,
matrix. Yeah, so Kevin, that's going to be, this makes sense.
Yeah. Yeah, so this O of alpha thing, I believe is, so this is like around D squared. Yeah. So, okay. So this is the, yeah.
Actually, so,
Mhm.
so how should we think about that matrix? Like, what does it represent?
Yeah, it's I think of it as a convex relaxation of So I think this is sort of like I made a proof that I could fit on a slide, and kind of there are more general approaches that are like a bit harder to like fit the whole proof on the slide, but I think they're kind of more general, and they, yeah, maybe I'll talk more about it in a couple slides. Yeah.
I guess maybe one thing to say is that you're trying to verify sort of, how much math, you have this unknown distribution and noise model, you're trying to verify things about it, certify things about it, so you can't assume things about it. Well, it would be nice if sort of the disagreement region of my candidate hypothesis and any other one is not too concentrated or anti-concentrated in any one region, as it would be with for example, that's what would happen in the Gaussian. So, you're looking at some sort of weighted covariance matrix and making sure that the data is kind of distributed in sort of a nice way, happens to be, I don't know. That's
Yeah, I mean, it's also, I think another way is to think it's a degree 2 sum of squares proof. So it's like, there's a proof that uses only this sort of degree 2 properties. Like after kind of you break it into this. Yeah, I think that's one way to think about it. It's like a degree 2 sum of squares proof that your thing holds. Okay. Yeah, and then recall that, so I showed you how to certify this property that allowed the multiplicative error here and only showed an upper bound. But what we wanted to certify is this more stringent thing, where this constant is super close to 1, and you not only have an upper bound on the fraction of points that fall in the region where W and W prime disagree with each other, but also have a lower bound. And I'll tell you a couple words about how that type of thing is certified. So what you can do, so the tester, describing the tester is not that difficult, maybe even easier than the tester I described earlier, but the analysis is quite a bit more involved. So what do you do first? You have this vector W that you're given, and you break your d-dimensional space into this little bands. So every band has so based on the inner product with W, and each band will have a thickness of around epsilon. And then you check for every monomial M of degree at most K. So K is some parameter, K is some large constant, that the average of monomial times the indicator of the band. So you do it for every band. So you look at the average monomial times indicator and compare with what this average should be under Gaussian distribution in expectation. So you compute these two quantities and you make sure they're super close to each other. So that's the test. Yeah, it's easy to show that Gaussian distribution will pass this test with very high probability. And if this degree parameter K is constant, the runtime is polynomial for this tester. And what we show is that if this test passes, then you have the fraction of points in this for every W prime, the fraction of points here, where the half space of W and half space of W prime disagree, is super close to what it should be under Gaussian plus epsilon. And this error here, the bigger you take K, the closer it becomes to 1. And the tools involved are, we use some sandwiching polynomials that are connected to pseudo-randomness. This method was introduced previously by Golovatek-Livens and Godard in 2023 for testable learning, for testing just the distributional assumptions of learning algorithms. And okay, so this is what you need, what you can use for testing RCN, testing the random classification noise model. And let me tell you a few words about what are the new ideas that come to Massart for Massart noise. So recall, so for Massart noise, you have with probability eta, the adversary gets an option to flip your label or to not flip your label. So if the adversary always makes this option, every time the adversary gets an option to flip a label, if it always takes the option, then what you get is RCN, is the random classification node. But the issue is that sometimes adversary might take the option to flip the label, and in some other regions, the adversary might not take the option to flip the labels, and that could lead to issues. And let me explain how, what that looks like. So overall approach is very similar. So you run one of those algorithms to get a good classifier. I see that you say, okay, I'm running this algorithm that assumes Massart noise. You get a classifier W. You again break your examples into a set where the classifier misclassifies it, gives the wrong label, and you check that the set is not too large, which should be the case if it's indeed Massart noise. And now again, there are these two quantities that we want to bound. So we want to certify, so this is the exact same thing we had for the previous algorithm in the RCN. And here, this is also like roughly the same quantity. So you want to, for every W prime, you want the fraction of points here to not be too large. Okay. Okay. The fraction in this S incorrect. But the only difference is it's 1 over, here we have 1 over this quantity that's here. So this is just to handle the case where the adversary just never ever chooses to corrupt everything. So that's the only difference. So these are essentially the same 2 quantities that we had a few slides ago. And the soundness proof is also essentially the same. So if you have this, if you are able to certify these 2 properties, then if you decide to switch, if you move from W to W prime, this first condition says you'll make a lot of extra mistakes. And this condition will tell you that you will not fix too many mistakes. So overall, you cannot gain more than epsilon in accuracy if you move from, if you choose your new half space to be some other half space W prime. So, and S is again.
So let's switch it. Making that a 0.49 instead of a 1, doesn't that change like a factor of 2?
Yeah, so this used to be expectation over S incorrect, and the size of S incorrect is 0.049. So this is it's like it is the same thing if you So that's it is the same thing. It could be smaller. Yeah. So for random classification noise, you end up with the same thing. Yeah. Yeah. Thanks for your question. Okay, and so here's where the Massart kind of, you have an issue with Massart. Yeah. So S, if your assumption holds, S is indeed Gaussian. So that part stays the same. So certifying this first thing is exactly the same. Is handled by the algorithms I already showed you. But what about this second condition? Yeah. So if your distribution is indeed incorrect, if your distribution is Gaussian and the noise satisfies the Massart assumption. So if it was the case that every time your adversary got an option to corrupt the label, it took the option, then this data set as incorrect would indeed be composed of a bunch of Gaussian data points. Yeah, the problem is that if sometimes this will no longer be the case if for some regions in space the adversary chooses to not corrupt, right? So what your data set as incorrect will satisfy is the following. So first, someone picks like this many points, 0.49 as points from Gaussian distribution. And then an adversary comes and deletes a bunch of those points. Yeah, so every time an adversary decides to not corrupt some point that it has an option to corrupt, it essentially removes it. This leads to this point getting removed from this set as incorrect. Okay, so what you want is you want to certify this property for some data set as incorrect. But before this data set, if the old assumption held, this data set was just a bunch of Gaussians. But now it's a bunch of Gaussians, except some points are deleted from the data set. So this is the task that everything reduces to. Okay, so you want this certification algorithm that is robust to deletions in this type of sense. So and also it's not hard to show that this band tester that I described earlier, there are ways to make deletions for this thing to just fail. Yeah, so here I just copied what the tester is. So, and you can check that, for example, if you delete the points for which some coordinate x1 is large, if you just go ahead and delete those, then the difference between these two things will be, so here you'll have, this is 0, and here it becomes some function of epsilon. So the tester will really fail. Yeah, these two quantities will be actually too far from each other. So you need some new idea what to do for this testing step. So this tester is not robust to deletion. So how can you make a different tester that is robust to deletions? So what you can do is the following, what we call the spectral band tester. So instead of looking at these averages, and just a piece of notation so everyone's on the same page. So x tensor k is just the list of values for your monomials m of x. Yeah, so the tester looks at the values of all those monomials, of the average values of all those monomials, and compares it with what it should be under Gaussian distribution. So what you can do, what we do instead is we look at this matrix. So again, you have a bunch of bands. You iterate over all bands, and you have an indicator for you just look at the things in the band. And instead of looking at the average of monomial vector x tensor k, you make a matrix of x tensor k times x tensor k transpose. So you make a matrix like that, and you average that among your data set you're given. And then you compare it with the matrix that you should get from your Gaussian distribution. So what does this matrix have to be if your distribution is indeed as Gaussian? And you add some error term as a margin of error. And again, you can show that if your distribution is Gaussian, then this quantity will be super close to what it should be in expectation. So the test will pass. And so one way I like to think about this test is what you're testing is that for all polynomials b of degree k, the average, average b of x squared times the indicator of the bucket. So like this quantity. So for each bucket, the average b of x squared is not too much bigger than what this average b of x squared should be for Gaussian. Yeah, so this is, yeah.
Can you finish in like a minute or two?
Yeah,
Okay.
sounds good. Yeah, I'm basically done. So this is what this tester does. Yeah, and this can be checked efficiently because it's an inequality between two matrices. And what we show is that if this tester passes for your data set, then for every vector w prime, the fraction of points in this disagreement region between w and w prime is at most something essentially very close than what it should be for Gaussian distribution or less. And we also show that this tester is indeed robust to deletions. And that's quite easy to check, because if you have this for a pair of matrices and you just remove an x from your data set as prime, then spectrally this matrix gets only smaller. Yeah, all diagonal. So the matrix you get here will be smaller than what it was here before you removed your point. So yeah, so that's pretty much it. And like one open problem I would like to underline is what about other data distributions? So can you have algorithms that will accept not just Gaussian but other probability distributions such as log concave? And what about algorithms that are tolerant? So can you have algorithms that will not only accept when your distribution is Gaussian and the noise is Massart, but also when, let's say, your noise is very close to Massart in total variation distance? So that's it for today. Thank you very much.
We have time for like one really quick question, but our son will be here for the next year or two, so you can meet with them as much as you'd like. But any questions? What if you wanted to do something beyond half spaces?
Yeah, great question. Part of it is a lot of the Massart noise papers are just for half spaces, and because it's been studied relatively recently in the context of computational learning theory. But yeah, it'd be very interesting to try to extend this to other classes such as intersections of half spaces and so on, or neural nets. Yeah.
Okay, let's thank Arsen again. Thanks.
Thank you.